Hello students, I am Dr. Naveen, Assistant Professor, Department of Electronics and Communication Engineering from BVRIT Narsapur campus. Today I am going to teach a VLSI subject on a particular topic, that is device fabrication and IV characteristics. So this is the device fabrication where you can fabricate MOSFETs like NMOS, PMOS and CMOS. So coming to the outline of this topic, so the first one is we will deal with the introduction. So in that introduction, we will discuss about the generation of your electronic devices, how it is evolved, and later what is the main reason there is a drastic change in our electronic devices, as you can see in our day-to-day life and also in the technology. At the same time, coming to the next topic, that is structure of the MOSFET. So before fabricating any MOSFET, particularly you need to understand what is the structure, how it will look like. So next we will discuss about the MOSFETs. Then coming to the next topic, so we will dive into the device fabrication and what are the steps which are involved in the device fabrication. So we will briefly discuss in device fabrication. Finally, this lecture ends with the device IV characteristics. So in the device IV characteristics, we will apply voltage, then what is the behavior of the current, we will see. At the same time, is there any modes which are present in your IV characteristics. So let's move into the introduction. So if you look into this introduction part, so where you can see from the generations, if you take an example from 1876 to till now up to 2022. So if you look into the 1876, the Bell telephone is invented, and after that every 10 years or every year by year, particularly in the 21st century, there is a drastic changes in your electronic devices. As you can see from, if it is in 1939, there is a complex calculator. Then after that, there is a personal computer invented, that is in 1971. Then it's coming to the laptop in the era of 1983. Then the first smartphones, as you know that the iPhones are very famous. Then if you keep on moving from past to the present, that is the devices, if you carefully look into the devices, the device size is drastically reduced. So the device size is drastically reduced only because of the one device, that device we call it as transistor. So the main purpose of reducing these sizes of these electronic devices, which is responsible for your reducing the size of your transistor. So the transistor, here if you see here, this is the transistor first invented by in the Bell laboratories by the three scientists. Those are William Shockley, Barradine and Barretine in the Bell laboratories. So then after that, you know very well about the Intel company. So the Intel company, if you see this figure B, there is already, you know that the Intel, the manufacturers microprocessors. If you see the microprocessors, the Intel 90 nanometers and Intel 10 nanometers, and the next generation is Intel 18 Armstrong. So if you see this, there is a drastic changes in the microprocessor technology every year, or there is a famous quote from the Morse, for every 2 years there is a chip, the transistors present or incorporated in a chip doubles for every 1.5 year, or you can say 2 years. So if you look at this image figure B, the Intel 90 nanometers to the Intel 18 Armstrong. So what is this 90 nanometers and what is this 18 Armstrong? Which means it is a future. Intel 18 Armstrong is a future. So basically it indicates the transistor we are reducing drastically in the form of reducing the channel length. So here the 90 nanometers, which represents the channel length. So the channel length, that is the 90 nanometers, and the future it is reduced to the 18 angstroms. Angstrom means 10 to the power of minus 10. So the Intel is predicting that by 2030, the chip, whatever the microprocessor or any chip, which consists of 1 trillion transistors. So this is the expectation from the Intel. So what is the benefits of reducing the transistor size? So benefits of reducing the transistor size mainly because of increasing speed and improve the performance and high integration density, which means more number of electrons we incorporate in the chip, and we can reduce the cost of the chip. So these are the main benefits of for reducing the transistor size by reducing the channel length. So this is a brief introduction about the transistor. So the main reason, you already know that how the transistor size decreases and we can incorporate more number of transistors in a chip. Next we will see the structure of the MOSFET. So basically you have studied already transistor, the transistor BJT and MOSFET. So there are two types of transistors, those are the BJT, one is BJT, another one is MOSFET. So but in electronic industry, particularly in our day-to-day life, what we are using, mobile phones, watches, personal computers, laptops and everything, they will use MOSFETs compared to the BJT. So I don't want to discuss about the BJT. I want to only concentrate on MOSFET, which are presently used in our electronic devices. So MOSFET, we call it as metal oxide semiconductor field effect transistor. Once again I am telling, metal oxide semiconductor field effect transistors. So we will discuss also how the name come to that transistor as a metal oxide semiconductor field effect transistor. So basically these MOSFETs are two types, one is depletion type, another one is enhancement type. One is depletion type, another one is enhancement type. So the depletion type further divided into N type and P type, and the similar way enhancement type, it is further divided into N type and P type. So based on the fabrication, we call whether it is a N type MOSFET or a P type MOSFET. At the same time, it is of two types. We told that depletion type and enhancement type. So whether it is in depletion mode or in enhancement mode. So as of now, I want to give the structure of how the N-channel enhancement MOSFET looks like. So first, to fabricate a transistor, particularly MOS transistor, so in the MOS transistor, first you need to select the substrate. So this is the substrate. If you want to fabricate the N-channel enhancement MOSFET, then you need to choose a P-type silicon substrate. You need to choose the P-type silicon substrate. You already know P-type silicon substrate, which is have majority carriers are holes and minority carriers are electrons. So after choosing the P-type substrate, next you need to diffuse the two heavily doped regions on each end of your substrate. So this is one region and this is another region. So these two regions which acts like a source and drain, then we will discuss what is source and drain. Next, you need to grow a silicon dioxide on top of the substrate. So first of all, you have selected the P-type silicon substrate, then you have diffused two heavy regions, both N plus regions, and the next what you have done is you have grown a silicon dioxide. So after growing the silicon dioxide, you have to remove these portions that we will cover in the fabrication. Then you need to do a metal contacts. You need to do a metal contacts, or you need to deposit a metal contacts. One is at this region, another one is at this region, another one is at metal region. or bottom of your substrate, and one is at your silicon dioxide above. So next you do connect the contacts. So these contacts we name it as drain contact, source contact, and gate contact, and substrate contact. So we will discuss what is these terminal names. So first one is the drain terminal. So in the drain terminal, why we call it as drain terminal? Because of the reason where your electrons will come out of this drain terminal. So that's why you call it as, name it as drain terminal. So why we call it as source terminal? So where your electrons will enter into the source terminal. So that's why we call it as source terminal. And next, the gate terminal. So the gate terminal, very important terminal. The gate terminal which controls the flow of electrons from source region to drain region. Once again I am telling, the gate terminal is very important. So it controls the flow of electrons from source region to drain region. It is like a tap. You know, if you open the tap, water will come. If you close the tap, water will stop. The same applies here also, but here for the gate you need to apply the voltage. Here for the gate you need to apply the voltage. That voltage will control the flow of electrons from source region to drain region. So, and the last terminal is substrate terminal. So, which is very important, particularly when MOSFET is used in the applications. As of now, I don't want to discuss this. So, because it is not covered in your syllabus. So, only we will discuss about this source, gate and drain regions. Now, you understand the structure of MOSFET. So, the structure of MOSFET, first one is the select p-type substrate, then diffuse the N regions, both N regions we call it as source and drain regions. Now deposit silicon dioxide, or on top of it you deposit metals. So metals which is used for acts like a contacts. So in the beginning of the MOSFET I told why it is called MOSFET, metal oxide semiconductor. So if you read the names of these layers from top to bottom. So the first one is the metal, and the second one is the oxide, and third one is the semiconductor. So that's why we call it as metal oxide semiconductor field effect transistor. So the why we call it as field effect transistor? So the flow of electrons which is controlled by applying a voltage to the gate terminal. So because of that we call it as metal oxide semiconductor field effect transistor. So now you understood what is the structure. So next we will go to device fabrication, which is very important to fabricate the MOSFETs. So the MOSFETs which are of depletion type or enhancement type, or we call it as NMOS or PMOS. So before moving to the slide, I would like to discuss one thing. So basically if you see, so the electrons which are flowing from, I said that electrons flowing from source region to drain region. Electrons flowing from source region to drain region, but if you see there is no direct connection between source region and drain region. So in such a case, the electrons does not flow from source region to drain region. So they imagine that you have not applied any voltage, to the any terminal, and there is a huge resistance between this source region and drain region. Once again I am telling, without applying any voltage to the any terminal, particularly gate terminal, there is no connection between source and drain terminal. So in other words, we can say that there is a huge resistance between source region and drain region, that we call it as resistance of 10 to the power of 12 ohms. So this is the silicon wafer. This is the silicon wafer where you need to fabricate millions of billions of transistors. Where you need to fabricate millions of billions of transistors. So if you zoom into it, I have taken only one tiny part, that is this MOSFET. That is a single MOSFET. So next we will move into the device fabrication. So coming to the device fabrication, there are main 8 different steps in the device fabrication. So the first one is wafer manufacturing, and the second one is oxidation, and the third one is photolithography, and the fourth one is etching, and the fifth one is ion implantation, and the sixth one is metal wiring, and the seventh one is electrical die sorting, and the eighth one is packaging. So out of these steps, so you don't have these 2 in your syllabus. So I will cover only up to 6 steps. So first we will go to the wafer manufacturing. So before going to the wafer manufacturing, I told you that in the previous slide, so this is the silicon wafer, this is the silicon wafer where you have fabricated millions of billions of transistors. So first you need to fabricate this silicon wafer. So in order to fabricate a silicon wafer, you already know and well aware that, and the silicon is the second most common element in the earth crust. It comprises of approximately 25 to 26%, and after that your oxygen. So the first place is your oxygen, which is of 49%, and the second place is your silicon. But the silicon which is not in its pure form, but it is in not pure, that is silicon does not occur naturally in the pure form. Need for electronic applications. Need for electronic applications. So the starting material for fabricating or manufacturing the wafer, that is your sand. That is the sand. The sand is not only sand, that we call it as silica sand. From the silica sand, we will extract the silicon. From the silica sand, we will extract the silicon. So as you can see, this is the silicon sand, silica sand. That silica sand, you need to convert into pure silicon. What we call the silica sand, which is converted into the pure silicon, that we call it as metal graded silicon. Metal graded silicon. The pure silicon which is converted by using this silica sand, that we call it as metal graded silicon sand. So which is not used for the fabrication of electronic applications. Then next what you have to do is, next this metal graded is converted into electronic graded silicon, which is of ultra pure. Which is of ultra pure. So first is sand, that is silica sand. The silica sand is converting into the pure silica, that is Mg graded, which means metallurgical graded, that is not suitable for the fabrication of your electronic application. Next you have to convert that one into the pure electronic graded, Vg graded silicon, which is very ultra pure. So in the next slide I will show how it will happen. So this is the one of the famous procedure that we call it as CZ method, where the silicon or metal graded silicon is melted. Then after that, by using the die, you want to extract this entire silica. So this silica we call it as electronic graded silica. Then this entire tube like structure we call it as ingot. So the ingot is first polished. As you can see here, first it is polished, then with the diamond cutters we need to slice it. Next you need to slice it. See here into the small wafers. So this is one wafer which is of millimeter size. So this is of millimeter thickness. So as you can see in the next slide, so these are the different ultra pure silicon where with the different diameters. So the different diameters are the inches in the range of 2 inches to 18 inches. 2 inches to 18 inches. So as I told you, there are two ways to convert the metal graded silica into electronic graded silica, that is with the CZ method, and another one is the float zone method. So these silicons, if you see here, there are different diameters of, we can say, which is range from 12 inches to 18 inches. It depends upon the application, and the silicon having a properties like it's a p-type and it consists of medium resistivity. At the same time, it is having 100 plane. So once again I am telling, the silica wafer properties to fabricate n channel MOSFET. So you need to select p-type substrate, which is this one is the p-type substrate, assume, and it is having a medium resistivity and it is having a 100 plane. So you know p-type silicon, which is of having majority carriers are holes, minority carriers are electrons, and it is having the medium resistivity. And coming to this 100 plane, so 100 plane, as we call it as a plane where your electronic devices are fabricated. A plane where your electronic devices are fabricated. So particularly we have to choose the 100 plane. There are other different types of planes, but for fabricating or the electronics will support, particularly if you want to fabricate in the silicon substrate, you need to choose 100 plane. So basically, if you say here, let us take an example. If you construct a house, you will see the vastu, and you vastu like which side the front door will come or which direction, and which side the bathroom will come. At this extra, everything will be there in. So the vastu. At the same, similarly, if you want to fabricate any transistors on the silicon substrate, so we need to choose the 100 plane. So that is about the silicon wafer. So silicon wafer, so you know now how you can fabricate or manufacture. The first one is take a sand, that is the silica sand, and convert into the metal graded silicon, which is of not pure form. Then it is converted into electronic graded silicon by using the CZ method or a float zone method. So these are the different sizes of your ingots. We call it as, this one as ingots. And if we want to fabricate a n-channel type MOSFET, we need to choose a p-type substrate, and which is of having medium resistivity with the 100 plane. Coming to the second step. So in this step, so after you have sliced this wafer from the ingot, after slicing the wafer from the ingot, so you need to grow a silicon dioxide on top of the silicon substrate. So here I am showing the image where you can see this is the silicon wafer. If I zoom into a small portion in this silicon wafer, so I have zoomed it here. So this is a small portion in this wafer where I have grown a silicon dioxide on top of the substrate. So basically the silicon dioxide, it is grown on this surface of the substrate. We can do in two methods. One is the thermal oxidation method, or we call it as wet oxidation, and another one is the dry oxidation method. Basically you need to send a water molecules onto the surface of this silicon substrate. The water molecules will react with the surface of the silicon and forms the silicon dioxide. It is a one method that we call it as a wet oxidation or thermal oxidation, and another method is dry oxidation. In the dry oxidation, you need to send a oxygen onto the silicon substrate, then it will forms it will grow a silicon dioxide which is of thickness which is of 1.5 nanometers. 1.59 nanometers. And the famous method which is used for grow the silicon dioxide on the silicon substrate is plasma enhanced chemical vapor deposition. Plasma enhanced chemical vapor deposition. This is one method. There are a lot of methods are there. So the main crucial role of this silicon dioxide, which is it acts like an insulator and it acts like a gate dielectric. At the same time, it acts like a interlayer dielectric. So which separates the silicon substrate from other materials, and it acts like a dielectric. So this is the second step. So the next step we will see, that is photolithography. So photolithography is the one of the very important step. So because there is no photolithography, so there is no transistor or particularly MOSFETs. There is no MOSFETs. In the photolithography, the first step is you have to deposit a photoresist. You need to deposit a photoresist on top of the silicon dioxide, which is we previously grown on the silicon substrate. Is grown previously on the silicon substrate. So what is the importance of this photoresist means? By using this photoresist, we can make a patterns. We can make a patterns. So those patterns which are helpful to fabricate your transistors or transistors, capacitors and resistors and etc. So the photoresist, which is very important process. So if you see here, these are the important steps in photoresist deposition on the silicon substrate. First of all, you need to have a spin coater. So this is the spin coater, as you can see. So in the middle, you need to place your silicon substrate, not a silicon substrate, the silicon substrate with the silicon dioxide grown silicon substrate. So then you place it here. Then after that, you will deposit a photoresist, or we call it as a dispense resin. So this, what will happen is, if you rotate this spin coater at 5000 rpm or 3000 rpm, so the dispersed resin on top of the silicon dioxide grown silicon substrate, it is uniformly distributed. It is uniformly distributed. So finally you need to dry this deposited photoresist on top of the silicon substrate at 60 degrees to 100 degrees. Then finally process is complete. So in order to understand this, so there is a video you can see here. So you are depositing the photoresist on the silicon substrate, then you are rotating it at a speed of 3000 to 5000. It is uniformly distributed. Then it is dried. Then it is dried from 60 degrees to 100 degrees. Then what will happen? It will attach it to the silicon substrate. Attach it to the silicon substrate. So the photoresist is the liquid. So because of that, we need to dry. So moving to the next step. So in the next step, we will discuss about photoresist types. There are two types of photoresist. First one is the positive photoresist. The second one is the negative photoresist. So in the positive photoresist, which is nothing but, if you see here, the light is exposed on the photoresist. The light is exposed on the photoresist. So the light make a chemical reaction with this photoresist at the particular place. Then that place is, or that photoresist is very sensitive. We can remove it with the chemicals. So which means, for the positive photoresist, if your light is focused on the particular place of your photoresist, that light which is chemically reacted with this photoresist, and we can easily remove this particular portion. So that type of photoresist we call it as positive photoresist. The light is normal light, not a normal light, we call it as UV light, ultraviolet light. On the other hand, there is a negative photoresist. In the negative photoresist, if light falls on the particular place of your photoresist, if you see here particular place, then due to the chemical reaction, it will happen due to the fall of light on this photoresist, and it becomes very tight to fix it to your silicon substrate. Tightly fix it to your silicon substrate, and the remaining portion is removed by using the chemicals. So now you understand what is the photoresist. So if you see here the photoresists are crucial materials in semiconductor manufacturing, used for patterning integrated circuits and other electronic devices. They are light sensitive materials that undergo chemical changes when exposed to light, allowing for the transfer of patterns onto the semiconductor substrate. As I told you previously, so the photoresist main advantage is we can fabricate transistors or any components like capacitors and resistors because of patterning these photoresists. And these photoresists are two types. One is positive photoresist and the second one is negative photoresist. So moving forward, the next slide is the heart of your transistor fabrication. That is your final step. You need to make a patterns. So if you see here, we only deposited photoresist, but how we can make a patterns like this? How we can make a patterns like this? Imagine at nanometer level or micrometer level. So we need to send a light of this nanometer length which is falls particularly on this photoresist, either positive photoresist or negative photoresist. How it is possible? Practically it is not possible. For that there are photolithography machines. One of the famous company, that is your ASML. The ASML which fabricates these machines, photolithography machines. So because of this photolithography machine, we can able to fabricate millions of billions of transistors. So I will play this video. You can see this is the this is the extended UV light. See this, the light is falls on the particular places in your silicon substrate. This is your silicon substrate. So if you want to make a patterns at nanometer level or micrometer level, so in this coming era is all transistor sizes are in the nanometers range. So we need to send the light of that much very thin, which is only possible with this ASML machines. So here what is the process, the complete process? If you look into this, first the UV light which is falls on the condenser lens. From the condenser lens, the light goes to the photomask. So this photomask, which is very important for making the patterns on this photoresist. This photomask, which is very important to make a patterns on the photoresist. So the photomask, the light falls on this photomask, and using the projection lens, what you are doing, you are transferring this light to the particular location in the nanometer or micrometer range. So if it is a positive photoresist, we can remove this portion, or if it is a negative photoresist, we can remove this portion. Positive photoresist which is used. So now you understand what is the photolithography. So the photolithography which is used to make a patterns on the photoresist by using this EUV light, extended ultraviolet light. So the next step is etching. So in the previous step, you have what you have done, you have chosen a specific targets or specific places in your photoresist where you need to remove. So the removing also one of the big tasks that we call it as etching. If you see here, the light falls on these particular places, then by using the etchants are the different chemicals which are used to remove this photoresist. So if you look into this, these are the gaps where you have removed your photoresist, or you can say the light which particularly falls on this place, you have removed this by using the etchants. That process we call it as etching. So if you see here, you can see this lengths of these patterns. That is all depends on you as a programmer, how much length you require on these patterns. So the etching, which is main purpose, is used to remove the photoresist by using the etchants. The etchants are nothing but there are different types of chemicals. So etching is an essential step in a semiconductor fabrication process that involves the selective removal of material from the material is nothing but your photoresist. Not only the photoresist, at the same time we can remove some cases your silicon dioxide also. So from the wafer to create a desired structure and features. This process is used to define the shape of the various components. As I told you previously, the patterns which are very important to create various components such as a transistor, capacitor and interconnects. By removing unmasked regions of the wafer, the desired regions of the wafer is protected by using the photoresist. If you see here, so we are removing this portion, but the other photoresist which is present, which means this photoresist is protecting silicon dioxide as well as the silicon wafer substrate. So these gaps or these patterns will helpful to create your transistors or capacitors or resistors, either interconnects. So the etching is of two types, that is wet etching and dry etching. The wet etching nothing but by using the chemicals you can able to remove these portions, either your photoresist as well as your silicon dioxide. The dry etching means we use a plasma technique to remove the photoresist or your silicon dioxide or material. So now you can able to understand what is etching. Next, coming to ion implantation. So in the beginning of the class I told you about the structure. So the first one is the silicon substrate. Next, for your understanding, what I have done is there I have deposited a N+ regions on both ends of the substrate. But actually that is not the procedure. First you need to select the silicon substrate, then you need to grow the silicon dioxide. On top of that, what you have to do is you need to deposit a photoresist to make a patterns. Then you need to remove those patterns by using the etchants. Then next what you have to do is you need to deposit N+ regions. Suppose if you are fabricating N-channel MOSFET, you need to select silicon substrate. Now if you see here, N-channel MOSFET, that is the silicon substrate. So next what you need to do is you are growing the N-channel MOSFET. So for N-channel MOSFET, you are choosing the silicon substrate. Then you have grown silicon dioxide. Then you have deposited photoresist. So by using the photolithography, you have removed a specific portions, and these portions which are very important for your fabrication of your transistor. By using the etching. So now the ion implantation means you need to deposit N plus regions. So look at this machine. Basically this is a low temperature process. So once if you choose the dopant, then you need to guiding through this chamber and hits at your silicon substrate. And whenever it's at the silicon substrate, only the unprotected regions, the ions will enter into this silicon substrate. So I will show on video, you can able to visualize. So the first is photoresist. Then after that, by using the photolithography, which is UV light, you are making the patterns. So you see here. So then you are using etchants to remove the portion. There you can see. So this portion you are ion implanting. So if you see here, it will form the N well. So the ion implantation means you are implanting the impurities inside the p-type substrate. Now I call this one as N plus region. So these three regions I told you that which acts like source and drain regions. So after implanting this N plus regions, the next step is the gate formation. As I told in the beginning, the gate is very important to control the flow between source and drain. So here you deposited a polysilicon on top of the silicon dioxide. Next, what you have to do is, again you need to do the photolithography to remove these portions. How you remove these portions? By using the etchants. So now this portion of polysilicon is remain. This acts like a gate. Again you need to use some etchants to remove the silicon dioxide, and finally you need to make a electrical contacts at this particular places. Now it acts like a MOSFET. So coming to the metal contacts and wiring. So here first what you have done, selected the silicon substrate, grown the silicon dioxide and diffused the N plus regions and deposited the polysilicon, and the sixth step is metal contact wiring. So in the metal contact wiring, what you have to do is you deposit a copper contacts on top of it. Again you need to remove these portions by using the chemicals. Then you connect the metal wires which is of aluminum, tungsten, etc. So the final step which is of your electrical die sorting. So the electrical die sorting, so after all these steps, so this is your millions of billions of transistors are fabricated in single silicon wafer. So if you see these rectangular boxes, so in these rectangular boxes which consists of some millions of transistors. Now by using the diamond cutter you can remove or cut these portions, and the single portion we call it as a die, and this is the final end product where we are currently using as a microprocessor or any other advanced chips. So the next step, which is of packaging. So after packaging, we are using in our electronic devices. So this is the complete process of your fabrication. So up to step 7, we have seen the fabrication process and the IV characteristics of your mass device. We will continue in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.